Good morning, ladies and gentlemen, and welcome to the last episode of Control Systems 2. I'm glad to see that some of you survived until now, which is a good sign. So today we're going to talk about a little bit everything of what we've done during the course, with a little bit of extra spice at the end. We'll just cover some maybe non-obvious, non-traditional topics that are nevertheless relevant to understand how everything we've been doing until now fits in the bigger picture of actually designing a control system. That is, what are the steps that one should take when you face an actual physical system and you want to try and implement any of the stuff you've been learning in the last semesters of control systems? Is there or not a standardized approach to actually go about and facing the design process? So we're going to do this general recap. We're going to focus in particular on the control synthesis part, but we'll touch upon everything else as well. And we'll talk about this control design process. And at the end, I plan on keeping this lecture short. I took several minutes off you every week, so it's just fair that I give you some minutes back at the end of the course just to break even. I don't want any of you to go back home and say, oh, you kept me afterwards, you made me study more than I had to. So, but I would I'll stay available until the end of the class and answer any questions you may have on a one-by-one basis. I was hoping, sincerely speaking, that you had posted more doubts, questions, and topics in particular that you wanted me to address in this specific lesson. Unfortunately, only one of these things was published on Piazza. We'll address that question, and at the end, if you have things you would like me to talk about, I will. If not, you would be free to go. So let's start from Adam and Eve. Every good story starts from the beginning. So what have we been doing in control systems, right? You started after dealing with the basics of math and physics and understanding your way around what's the basic language of this game. You started studying control systems in the Control Systems 1 class. And in Control Systems 1, of course, the first stuff you saw was related to how do we model systems, in particular how we do linear time invariant, single input, single output systems. You started looking at the fundamental topics of control systems, in particular how to play around with the different signals that are involved in a feedback control loop. And you saw what was the importance of these frequency domain mappings between different signals, these transfer functions, right? And you were told, look, this is how you can derive the transfer functions, this is what they mean, and look at how many interesting properties of the closed loop you can extract from these, from specific transfer functions, from analyzing like poles and zeros of specific transfer functions. And you then realized that although we were restricting the domain of analysis to this very particular case of single input, single output, linear time invariant systems. It seems like, in math, typically, when you need more than two adjectives to describe something, it means you're getting in the sub. Now, how relevant can it be? But actually, it turns out that it's kind of relevant because in the real world, pretty much everything, all the processes that we want to study are indeed nonlinear. But it makes sense to approximate these the behavior of nonlinear systems around specific operation points with a linear behavior. So it's always possible to approximate nonlinear systems around specific points with linear time invariant systems, and that's why they're very famous, they're very studied, and they're very useful as well. Of course, you were studying the very beginnings, so you focused on what happens if everything is perfect, right? So if you have the perfect knowledge of the plant or the process you want to study in particular, so you didn't really address any issues of robustness or model uncertainty as we did in this class. You were then introduced to the fundamental topics of why is a controller useful, and you were provided some tools, some analysis and synthesis tools. So the analysis tools are the ones you need to check if the controller that you have developed actually meets the specifications that are desired. And you saw in particular approaches like the Bode plots, like Nyquist diagrams, like the root locus, and things like this. And then you were given some tools to actually synthesize controllers. So if I give you a plant and I give you some specifications that you want your, for example, output to meet, then how do you go about and actually design a controller? So you strong of the fact that you now knew that this frequency domain hides like the important information that is going on in the control system design process, the first approaches that you saw were related to this concept of loop shaping. Now, loop shaping is how do I affect directly the transfer functions in the frequency domain? How do I shape those directly? And this is useful because we saw that many of the important properties of a control system, for example, disturbance rejection or noise attenuation or tracking or even stability, depend on some critical specific transfer functions, the sensitivity functions of the loop. So you saw like approaches like lead lag compensators, and then you studied PID control. Now, PID control is, to date, arguably still the most used approach to do controls in the real world in industry, because it works, and that's kind of enough said. It's easy to tune. It doesn't require much of a modeling effort. It's output feedback, so as long as you measure what's going on, and having measurements is the basics. If you don't have measurements of the outputs of the variables you want to control, there's really little you can do. And one just can go just about and turning 2 or 3 knobs and up to when you obtain some decent behavior for your system. So PID is extremely successful, and it's very practical. And then you were introduced to concepts of that were described as nuisances. That is, things related to the implementation. So how do you deal with actually transposing all these concepts that we've learned on our computer? How do you deal with the natural latencies or time delays that come either from the process or from the implementation? And other things like when you have saturation of actuators, if there are ways to avoid that, like the anti-wind-up schemes. So in control systems too, we stepped it a little bit further. So now we knew what was going on at a fundamental level, and we moved on in a couple different directions, mainly. First, we extended the domain of analysis no longer to single input, single output linear time invariant system, but to MIMO systems. So multi-input, multi-output, always linear time invariant systems. It's critical to remember that we're always dealing with linear time invariant systems. And the other direction that we moved in was that of uncertainty. So in practical situations, it's actually very tough to know what the model of the plant of the process you want to control is. And this is more true the more the plant becomes complex. So when you study MIMO systems, you reasonably think of a more complex plant because you have more channels, more sensors, more actuators, more things going on. And they're having a reliable mapping between all these inputs and all these outputs, that is the transfer function matrix of MIMO systems, is a little bit more complicated. So in face of this uncertainty, which we saw can be modeled in many different ways, nobody really knows what's the best way to do it given a specific circumstance, but there are many different uncertainty parameterizations. We introduced this concept, we looked at a little bit more in detail at the concept of robustness. So the concept of robustness is if I design a controller for a nominal plant, will it still work for the perturbed plant, for the uncertain plant? And when you have uncertainty, you don't really base your design on one plant, you base your design on a family of plants. And so how do we deal with the guaranteeing stability and performance, which are the two most important things at the end of the day, when you have these family of plants? Now, so you want your controller, your nominal controller, to work in all different circumstances. And this robustness, this uncertainty principles are important because not only it's at times difficult to identify, that is the model of a system. Identification is a technical term to say mapping the input-output relationship of a system. But then there's even natural things like the parameters that define a model might change in time due to, for example, aging of components. If a system just continues going on and on, and operating as nominally, eventually some of the components will wear off and things like this. So there is a bounded variation in the parameters that describe the system model. So we then once we understood what the objectives of a controller were, we said, okay, but what stands in our way? Now, every time you want to deal with a problem, you first understand where you want to go. Then you understand the objectives. Then you understand what stands in your way. What are the limitations? And then you figure out a way to actually, an algorithm, a way to actually deal with the problem. And then finally, you deal with the implementation. How do I put the algorithm, the solution of my problem, into actual practice? So speaking of the constraints, of the limitations, we saw that there were two big families of limitations. One was fundamental limitations, and the other one was more real-world, practical implementation-related limitations. And specifically for the fundamental limitations, we saw that depending on the systems we want to control, some are more tough than others, right? There is the famous saying that you can't make a Ferrari out of a sedan, right? So even with the best control system in the world, not everything is possible, right? So why? Because there are inherent fundamental limitations in controlling a system. Some might come from the presence of time delays. They might come from the presence of non-minimum phases zeros. They might come from the simple fact that there are constraints between the fundamental sensitivity functions in a loop that describe the behavior of the performance of a system. We saw that when we require, for example, disturbance rejection or noise attenuation, well, those are both related to some specific properties of the sensitivity functions and the complementary sensitivity function. But we know that these functions have two constraints, both at specific frequency points. That is, they're complementary, so their sum has to be equal to 1. So you can't really modulate both. If you decide the value of one, then implicitly you have decided the value of the other one as well. And plus, there are some global constraints over the whole frequency domain. And you remember the Bode integrals, so this waterbed effect, the idea that you can't arbitrarily shape the sensitivity functions. The more you push somewhere, like a waterbed, the more it pops up to the other side. So the more you try to reduce the gain of a sensitivity, the magnitude of a sensitivity function at a specific frequency range, the more you have to add dust, we called it, somewhere else. We called this the principle, it wasn't we that we called it, somebody else called it, but it's known as the principle of conservation of dust, right? So it's always nice to have principles of conservation in disciplines because they kind of make it more noble, right? We're cooler control systems because we have our principle of conservation. So, and then there were practical limitations related to mainly the idea of sampling and the idea of discrete time implementation. When you put all our continuous time system analysis, when gets actually put into a microcontroller in a computer, well, computers don't have the slightest idea of what continuous time is, right? So if you don't know what continuous time is, you can't possibly implement the concept of a derivative. If you can't do derivatives, you can't really do the differential equations, which is kind of the whole deal of a linear time invariant system, is a nth order first order ordinary differential equation. So these differential equations, these derivatives, are substituted, approximated with finite differences. And we saw that this brought to a number of problems, approximations, depending on the methods we used. And the idea that a computer only has knowledge of what is going on at specific time instants. And the time domain is sampled based on some arbitrary external clock that tells us when to evaluate things. So in the process of moving between the continuous and discrete time domain, well, there are some issues going on, both in terms of approximations, because of course we're losing, so to speak, information. And then there are some situations in which information is actually lost without the so to speak part, in the sense that if you have a signal that is varying with a certain bandwidth, that is, it has some, we can imagine the frequency content, the bandwidth of a signal to be how fast it can vary. So we notice that if we sample a continuous time signal not fast enough, then it's impossible from the samples to actually reconstruct the continuous time signal. This was the sampling theorem, the Whittaker-Kotelnikov-Shannon theorem. And so we noticed that, well, when we passed into actually implementing things, we might want to consider exactly what is this clock that has to, what's the sampling period or frequency that we have to use to measure what is going on in our system. And if we fail to use a sampling frequency that is fast enough, then we will lose information on the process, and therefore there is this back and forth, which is something the designer needs to be aware of. So we finally then, looking at MIMO systems, we noticed what? We noticed that the biggest issue that MIMO systems are this idea of having multiple inputs and multiple outputs, of course, as the name says. And in particular, the challenges in analyzing and synthesizing controllers based to it come from these interactions, right? The interactions between the different channels. And these interactions, there are many ways to characterize them. We introduced some fundamental ways that to measure these interactions that we call the relative gain array, and through that we understood that we could have a first hint in which direction to move to go towards synthesizing, for example, a controller. But before doing that, we went through the usual scheme that we did in Control Systems 1 as well, and we looked at, okay, what does it mean for a MIMO system to have a stable or a performant behavior? How do we analyze this behavior? And we introduced a number of tools, similar to the ones we used in Control Systems 1. Similar in the sense that they eventually go and evaluate and measure the same concepts. Now, it's all about the sensitivity functions and how the different signals in the loop relate to each other. It's only that when you do MIMO systems, you have more signals. These signals are a little bit less straightforward. So we had to introduce some different tools like the small gain theorem or these Lyapunov functions to evaluate stability. We had to factor in robustness in some way that might have not been so straightforward. When we did it, we talked about structured singular values, or these mu parameters that go and measure how much does the uncertainty on the different channels affect the performance of a system. And then we said, okay, now that we have the tools to assess if a controller for a MIMO system actually meets the specifications, how do we go about and design a controller to do this? So, as I mentioned before, after evaluating the different relationships or couplings between the channels through the relative gain array, we could say, okay, look, if the channels are decoupled in the sense that there is a diagonal dominance in the relative gain array. There's some inputs can be paired with some outputs in such a way that the other inputs and outputs don't really affect that special relationship between particular inputs and outputs channels. Then we can consider a MIMO system basically as if it were a bunch of CISO systems put one after the other. So we can close the loop in around each one of these channels. Unfortunately, I mean, it doesn't. The general case is not always true. So we said, okay, what if it's not true? Can we always, what can we try and reconduce the complicated problem of having an interactive situation to one that is diagonalized, non-interactive? So we looked at these ideas of decoupling control, which is based on notions of feed-forward control, and the notions of feed-forward are always the idea of how do you make a brick wall fly, right? So pretty much whatever you have, like a brick wall, if you do feed-forward and you do the plant inversion, that is, you just divide it by a brick wall, then you can remultiply it by anything else and you get what you want. And this is a very powerful idea when it works. And unfortunately, it works only in the easy cases. That is, when you have a perfect system model of a system, knowledge of the model of the system, and the system doesn't behave in a funky way. That is, it doesn't have delays, it doesn't have non-right half-plane zeros, and things like this. So when these simple, let's say, straightforward approaches to designing a controller for MIMO systems don't work, what can we do? And that's where we started looking at, if you want, the more substantial part of MIMO control. which are these let's say, centralized or fully MIMO controllers. And we noticed that we literally transitioned between a design that was based on, let's look at the sensitivity functions, and here or there we want the bump or not, let's add it with specific terms, to a more formal, let's say, computer-driven approach to deriving these controllers. And I say computer-driven just because we don't go and design the details of the controller, but we focus on high-level, let's say, macroscopic performances. For example, we say, okay, well, we want our system to, our controlled outputs to track some specific reference signals. Let's focus on that. Let's say we studied the infinite horizon linear quadratic regulator problem. That is, suppose we want to just define something that is a cost, something that is we want to minimize, something that is ugly and we want to get rid of. We define this cost function over an infinite horizon, and we sum up things that are undesirable. For example, tracking errors, or for example, cost of the input, or the input effort, call it as you wish. And so we saw that if we set the problem in a way of saying, look, let's just minimize this cost function, then this whole machinery of optimization led to a specific solution that was based on ideas of state feedback, and one could automatically, without dealing too much with the weeds of the calculation, generate this nice control machine that would provide the desired performances in an optimal way, which is very nice. Where optimal, of course, doesn't really mean that you are doing the best thing possible, because otherwise we won't have a job anymore. But it's about, optimal is always related to the cost function. You change the cost function, you get a different optimal controller. When we saw the solution that came out of the linear quadratic regulator, and the solution being the input structure that solved this optimal problem, we didn't impose anything. We didn't say, hey, I want my input to be like this. Let's see from this structure what are the actual values that particular parameters get. We just noticed that the solution was this state feedback. Was based on feedback, was a u that was minus kx or something. And so we asked ourselves, okay, but the state feedback concept is really powerful. Why is it powerful? Because it allows us to affect directly what is the behavior of systems by literally taking some critical quantities that drive the closed loop behavior, that is the poles of the closed loop transfer function, and we could place them. We could do pole placement. This is whatever it is that is your natural behavior, I just remove it and substitute it with whatever I want. And that, of course, is very powerful because, in theory, in the ideal case, allows us to have arbitrary performances in our control loop. Unfortunately, we noticed that this is possible in some particular situations, and that is, in particular, when the system is controllable. And most importantly, we noticed that states, by definition, are not actually available to the control designer. A system has inputs and outputs. Outputs are what we measure. Inputs is the commands we send in the signal. The states are more like some hidden variables that contain the necessary information to relate to the inputs and the outputs. So a question naturally arose, and it was, okay, but so if we saw that these states are so powerful in doing feedback and we don't have them, how can we figure them out? Is there a way to reconstruct these states on the fly? And so we opened up the field of state estimation, and we looked at some famous results, in particular the Leuenberger observers, and we touched upon the beautiful Kalman filter. So we said, okay, if we put these things together, that is an observer and an LQR, so we're done, right? Because we get this automatic machinery that does everything we want to do, and we actually have access to the information we need to get this working. It turns out, though, that the LQG, the linear quadratic Gaussian regulation problem, while it guarantees the stability, while it actually does work and it's implementable, it's very model-based. It cannot guarantee robustness. So not guaranteeing robustness doesn't mean that it's never robust, but it means that it's not as powerful as we hoped it was. And so we moved forward and we asked ourselves a question, okay, but is there another kind of control approach that has the same desirable properties of letting us focus only on the high-level things, but guarantees robustness as well? And the Claudio talked to you about H-infinity control, which is based on this very idea. And finally, we touched upon nonlinear systems. That is, we said, okay, we did the linear time invariant, meme or seesaw, but what if instead the system that we're trying to control is such that it's actually too coarse of an approximation to just linearize it around operation points, because maybe its dynamic is so fast that that a linear approximation simply doesn't provide the justice to the dynamical behavior of the system. Well, so we looked a little bit at nonlinear systems and how to control them. In particular, I think a very powerful idea of nonlinear systems is that it's always following the same concept. When you deal with a new problem, well, the first thing you should try is just reconduce it to an old one. And we saw that there is this concept of feedback linearization in which, through some particular transformations of the inputs and the outputs, you can actually create an inner loop in a nonlinear system that provides a linearized behavior between inputs and outputs without doing any approximation. And that was really, really nice. So I pretty much talked about all of this already. A quick recap on a little bit more the math. So what was an LQR? An LQR, again, was based on this idea of creating a cost function. If we have a cost function, we can pretty much put whatever we want in it, but we weight different terms. In the regulation problem, which is that of following a zero reference signal, we just look at the controlled outputs that are different from the measured outputs. Remember that sometimes you get to measure things because of the physical constraints of a system. You have some sensors that you can place only in specific places, and you measure what you measure. But your interest might be different. What you want to control as a designer might not be exactly what you measure. So there's this distinction to be made between the controlled outputs and the measured outputs. And then the input effort is always important. So the problem was posed in finding a input sequence in the time domain. Note that we're moving from the traditional classical approaches of loop shaping, of designing the control system in the frequency domain, to a more signal-based time domain approach. And by cranking through the math, in particular through some nasty algebraic Riccati equations that required us some time and detail to go through, we saw that the input can be expressed in this way, which is basically a state feedback, as we mentioned before. So why is a linear quadratic regulator powerful? Because, of course, it's optimal in the sense of the cost function. It is very robust in the sense that it has guaranteed stability margins. This is very nice because it means that if you're not really sure about what the plant of your model is, you still can get pretty good results. We noticed that, additionally, it was under some simplifying assumptions in particular, this robustness condition holds when one of the terms of the cost function is considered to be zero, that of the mutual interaction between the states and the outputs. In particular, this x transpose n u term here. It's considered always a wise design choice to put that n to zero, so to gain this guarantee on the robustness. Of course, this desirable property of this LQR approach is that it's easy to tune. It's very similar to PID. Now you have your two knobs, you just play around with them. The designer doesn't really need to worry about if the outcome is something that will send your system unstable, because stability is guaranteed, and so it's a fun approach. But the problem of the LQR, as I mentioned before, is that of the state. We do not simply have, it's a very theoretically nice story, but it's not implementable unless we are lucky enough to be controlling a system where we measure actually the states, which is absolutely not the case in general. So we introduced this concept of estimation. We looked at the first important class of estimators, the so-called Leuenberger observers, we mentioned that an observer and estimator are pretty much the same thing. The estimation problem is, in general, a little bit more broad in the sense that the fundamental idea of the problem is, let's suppose we have the knowledge of a model of a system. Let's suppose we have the history of the measurements and the inputs. Can we reconstruct the states? And the question is, can we reconstruct the states when? Do you want the states now at this specific time instant? Do you want the states in the past? Do you want the states in the future? So depending on how you change this detail of the problem formulation, you'll find, details so to speak, you'll find in books terminology related to smoothing, if the states you're interested are the ones in the past, to prediction, if the states you're interested are the one in the future, or estimate or filtering, they're called, if what you want is the states at this current time instant, which is the case of interest to us. So an observer or a filter are synonyms, and loosely speaking, when you say an estimator, you mean a filter, although estimation technically is a broader term. So what was the idea of the Leuenberger observer? The idea of the Leuenberger observer was we need to find the states, we need to find them on the fly, and we create a numerical copy of the system. So what does that mean? It means like we just say, because we're strong of the knowledge of the system model, that's a very critical assumption. And well, if we have a system model, we don't know what the state variables are, but if we know the inputs and we match the outputs, then necessarily whatever variables are evolving in the middle must match what the ones of the original system are. So the key idea here that we borrowed from internal model control, which we looked at when we were trying to understand, to generalize the decoupling MIMO control approaches, was to feed back to this machinery, this numerical copy of the system, an uncertainty signal. That is the difference between our actual measurements and a prediction of what is going on. A prediction is always model-based. Now, this is the fundamental key idea in general. If you have a model of a system, a mathematical model of a system, basically you know everything there is to know if your model is exact. You can know the past, the present, and the future of everything. There are some phenomena that are really well understood. For example, I don't know, gravity and how planets go around in the solar system. We can predict eclipses or things like this with astronomical phenomena, 100 years of advance, right? Because we have a good model of what's going on. So if we feed back the difference between a prediction, what we expect things to be, and the actual measurements, then it turns out that it's provable that this Leuenberger observer, this numerical copy of the system, eventually will converge to the real states of the system. That is, the estimation error goes asymptotically to 0. And asymptotically is cool when you do the proofs of your theorems, but it means at infinity. And as a famous economist that I used to say, the long term, we're all going to be dead, so that this thing works in infinity doesn't really matter to us. So we asked ourselves, well, can we actually treat it as if it were a pole placement problem? In the sense, can we check if, can we design the Leuenberger observer such that the states estimates tend to the actual states with a dynamic that is designable? And it turned out the solution to be pretty beautiful in the sense that it was the dual problem of pole placement. It's exactly fundamentally the same thing as long as you switch a few matrices around. Instead of considering the A and B matrices of the pole placement problem, you consider the A and the C matrices in the observation problem. And that's intuitive, it's natural, right? Because pole placement is about control, right? So if you want to control a system, you want to drive your system where it needs to go, well, x dot equals ax plus bu. Your inputs come through the matrix B. B is a mapping between how do your inputs affect the states, the x dot, right, the state evolution. So when you have to do pole placement in the control problem, you really need that the A and B matrices satisfy some properties, which we call the reachability or controllability. When instead you're trying to reconstruct the behavior of the states as they evolve, well, it matters what you see, not how you can poke the system, but what you can measure. So the measurements come out from the y equals a cx. So it's the C matrix that at that point becomes relevant. And in fact, we saw that the same concept fundamentally, the dual concept of controllability that involves the A and B matrix was that of observability that controlled that, or detectability that involved the A and C matrices instead. So strong of, what was another very important concept that we discovered? We discovered that, okay, observers are really nice. They work in this beautiful dual way with respect to what we already knew on their own. So what happens instead if we plug them in the loop? What happens if we're trying to control a system through state feedback, but we don't know the states, and we are estimating the states as we are trying to control them? Okay, so what happens when we put together an estimator in the loop with a feedback control, with a state feedback control system? Well, all options were up to grabs, right? We don't really know if there were interactions or some funky phenomena coming out. And what we derived was this concept of the separation principle. That is, that the properties of the closed-loop system, having both an observer and a state feedback controller, were separated, as the name says, in the sense that there are no funky interactions going on. The designer can just worry about designing the observer and the controller independently, as if we were looking at the individual problems, which is really, really, really nice because it removes a lot of potential headaches. And so we defined this rule of thumb. We said, look, so how fast do you want your state estimates to converge to your states? Now, if we think about it intuitively, now, we care about the controls. That's the objective. We defined the objective at the very beginning. We said, objective is having a system that is stable, performant, robust, and whatnot, right? So control is what we're here for. This estimation was necessary to leverage the power of state feedback and get the control to work. So ideally, we would like to have the state right away. So we want the estimator to have a dynamic that is faster than that of the control. And therefore, we just threw out there this rule of thumb, and we said, we'll place the poles of the observer to be at least 10 times faster, an order of magnitude faster than the ones of the system. The idea being that you want the transient of the estimation error to die off quickly respect to the dynamics of the controlled system. So now that we understood that there was a way to estimate systems, the state of the systems, how does this fit into how does this fix our problem that we had with the linear quadratic regulator? So how can we use this optimization-based problem formulation, but plugging in a state estimator as well? So by solving the dual problem of the linear quadratic regulation, that is, instead of doing a least square based approach on the control side of things, we did a least square based approach on the estimation side of things, and we found that the optimal solution for estimating a state under some specific conditions, linear time invariant system that has some special, let's say, noise distributions, process and measurement noise distributions, they have to be Gaussian and zero mean. We found that the optimal, the best possible solution you can get under these assumptions that are very common and are relatively, let's say, easy to be verified, is this machinery called the Kalman filter. We, by no means, had the opportunity to delve into the actual details of a Kalman filters. Kalman filters are one of the strongest possible results one of the strongest results of estimation theory, control system theory. They work in practice, they're beautiful. We could do a course only based on that. There are actually courses based only on that, and I mean, that and various variations on the theme. I strongly recommend you to study in detail Kalman filters and, in general, recursive estimation as you move forward with your studies, because it's an invaluable tool to get things to work. Ducky bots run a Kalman filter to get the estimates of their states in order to control themselves, okay? It's not exactly a Kalman filter in the sense that a Kalman filter it works for linear time, for linear systems, okay? So a linear system is when, now you know a little bit about nonlinear systems, right? So what is a nonlinear system? How is it different from a linear system? Well, because it's not x dot equals ax plus bu, x dot equals f of xu, right? It could be anything. And same goes with the output equation. It's not cx plus whatever, but it's a g of xu, right? It could be anything. Well, a system is nonlinear even if only one of these two equations is not linear, okay? So for example, if you have, we said before, now given pretty much any physical dynamics, you can always approximate it as a linear system around some neighborhood, some operating conditions. You might be doing some approximation errors, but they might not be relevant for practical purposes. So let's suppose we have an x dot equals ax plus bu linear time invariant equation that describes the motion of a ducky bot, of a robotic system, or a platform, for example, a ducky bot. But the output equation, there's no way in the world it can be linear. Why? Because we're using cameras, okay? A camera is the only sensor you have on that robot, and a camera is not a linear sensor. It doesn't provide you measurements that are linear with respect to the state. There is much more involved there, and in fact, you should very well go and sit in a computer vision class to understand what's the relationship between the measurements and what is going on in the actual world, to understand the behavior of a camera. So a camera is a very nonlinear equation. So a ducky bot doesn't run a Kalman filter, but runs the nonlinear version of a Kalman filter, which is called Bayesian filter. So Bayesian estimation is the general field of nonlinear recursive estimation, which is really, really, really important, and it gets things to work. So finally, having this regulator, this nice implementable estimator that we can, that is even optimal in the sense that it finds the best possible estimate given these assumptions we've mentioned, and we can plug it in the linear quadratic regulator implementation, and what do we get? We get the LQG, which is the linear Gaussian linear quadratic Gaussian regulator. So it's linear, of course, because it deals with a linear time invariant system. It's quadratic because it solves a cost function that it's quadratic. It's Gaussian because Gaussian are the assumptions we're making on the noises that act on the system. So by just putting together these two things, we get LQG. It's just an LQR in parallel with a Kalman filter. The separation principle applies in the same way. Beautiful, elegant solution. We can just design the two things independently, and we get a Kalman filter basically is a Leuenberger observer, has the same structure. It's just that the gain that multiplies the uncertainty that we feed back to it is different, and it has a specific formulation. I would like to stress, as I did in the notation here, that we talked about the infinite horizon problem. So we just pretended everything was going at steady state, okay, which is the easiest way to deal with the problem. But the big power of these filters and this whole problem could be posed in a different way, such that the gains are time variant. So at every time instant, you update your gains to get an even better behavior. In order to do that, there are fancy numerical considerations that have to be done. You'll see them in the future, but just keep in mind that this is the easiest way to formulate the problem. But it shows what is the key ideas behind it. So in summary, what can we say about the linear quadratic Gaussian regulator? It's very nice in the sense that it provides, again, an optimal solution. It's implementable in the sense that it automatically generates the information necessary to have this state feedback control. But the funny thing was that although the linear quadratic regulator, the LQR, on its own was beautiful in the sense it provided great stability margins, and the Kalman filter itself on its own, since it's basically the same thing as a linear quadratic regulator, but the dual problem on the estimation side provides beautiful robustness margins, if you put them together, it turns out that you cannot guarantee robustness. There is no way to prove that if you do something in particular, you'll guaranteed obtain robustness of your controller. And this is not always a problem, in the sense that it might very well be that it works. But in some circumstances, it's a huge deal. So two things to say here. First, if you ever do an LQG and you design an LQG and you want to actually use it in your life, test it before you use it, okay? Design it, test it in a pilot plant, in numerical simulations, whatever you want. Perturb the plant as much as you want and understand what the bounds of the functionalities are, and then finally use it. So we gained some points. We're going in the right direction. We have a control structure that can deal with complex systems that have interactions between input and output channels without getting too much in the weeds of the design. We can focus only on, oh, time to break. You guys, you have to say something when it's time for the break. So we can continue later. Okay, so we left off noticing that this linear quadratic Gaussian regulator was nice, but it cannot guarantee robustness. And there are some situations in which robustness is really important, right? Because we understood that modeling exactly a plant is not something that comes in handy in all cases. So dealing with model uncertainty is a fundamental problem that needs to be addressed. So we asked ourselves, is there a similar mechanism, a similar approach to designing a controller that allows us to focus always on the big picture without delving too much in the weeds of the design process, but at the same time, it can guarantee robustness of the control system under all possible circumstances, under all possible plants that belong to the uncertainty set. And Claudio talked to you about this idea of H infinity control, where the infinity comes from the idea that we're basically solving the same, or at least the framework for the problem formulation is the same as for the LQG. We have a cost function, we have something we want to minimize, and the result just comes out of this minimization approach. But instead of using two norms in the cost function, we use infinity norms. And we've seen that infinity norms represent the maximum possible value of the biggest singular value of a transfer function over all the frequency domain, right? So we know that singular values are the equivalent, are the concept of gain, basically, for a specific input-output direction. And we know that these gains are important to be kept under specific bounds in order to guarantee, for example, stability and performance of a system. And therefore, having a minimization-based approach that relies on evaluating infinity norms of some quantities guarantees that worst-case scenarios are met. So again, the H infinity problem has many variations. The problem can be set in different ways. We looked at the so-called weighted mixed sensitivity approach, where the cost function is the infinity norm of a transfer function that includes different sensitivity functions of the closed loop that are weighted in particular ways. So instead of having the weights as we had before in the time domain in the two-norm cost function, now we have these weighting functions in the frequency domain that are used to shape the sensitivity functions in desirable ways in order to obtain performances and robust stability and robust performance for a system. So H infinity control works in practice, is based on the same framework of H2 control, so it's based on the same framework of the LQR. It's nice because it's based on, at least the formulation that we presented, recalls a lot of the classical ideas of control, of loop shaping. So it's understandable what is going on. But at the same time, the machinery that goes on behind it, the mathematical passages, are not straightforward. So it's to be treated often as a black box, and one needs to rely on the computer implementation. So if you remember at the first class, when we showed the Bode integrals, we said, look, at the end of the day, all control systems could be seen as taking shaping the sensitivity function, taking dirt away from some specific frequency ranges and applying it at somewhere else. And these were like old ideas in controls, right? So we went through all this process, through decades of research and then crazy math and stuff, and where did we get to? We got to basically the same thing, but now we're using a very formal synthetic machinery to do the same thing as we were doing before, okay? So don't lose sight of the forest because of the tree. Don't focus too much on the tree and miss the fact that you're in a forest. We went through all these details, but we're always doing the same thing, okay? We're always shaping sensitivity functions in order to guarantee that the specific properties like disturbance rejection, tracking, and noise attenuations are met. It's just that we're doing it in a much fancier way. And of course, doing it in a much fancier way is fancy, it's nice, but it has some inherent risks. And what are the risks? The risks are from the perspective of the education of control engineers, in the sense that we tend now to rely more on just plug in the numbers on a computer, sit in your control room, run all your fancy algorithms while something else is taking care of actually making things work, right? So there is a growing, let's say, detachment between the theory and the practice, and this was highlighted in this paper, it's a seminal paper in controls. I recommend that you all go and read it or watch the nice YouTube video about the professor that is giving the talk explaining these things. It's one of the things you need to be careful of, okay? Math is nice, it's very important, it's beautiful to do proofs. At least it is for me, I guess, maybe not for all of you. But it's important for a control system engineer to remember that the final objective is controlling a physical plant. And it's important to remember that although control systems are not maybe the most shiny of disciplines, with respect to the other engineering, like mechanical engineering or and aerospace engineering, things like this. You don't get rockets. Nothing would work without control systems, okay? It's like the secret technology behind everything. And if a control system doesn't work, bad things happen. Things explode, people die, bridges fall, shuttles explode, things like this, okay? So it's really, really important, like an act of responsibility, to make sure that you have a feeling with the physical plant and you ensure that the physical system actually works. So, okay, we did maybe a little bit too long of an introduction on what have we done until now. This was the part where I wanted to address your questions, but since I didn't get many, I'll just go about and say, well, very nice. We have all of this knowledge now. What are we going to do with it? How does it fit in the bigger picture, right? So in particular, let's say that I come to you and I give you a ducky bot, I give you a plant, I give you a process, that's a physical system that I want you to design a controller for. Right, so how does the whole control design process work, right? Apart from the how do these analysis and synthesis and modeling and stuff that we've been talking about up to now fit in the control design process? So suppose that you're given a plant. So there is a standardized procedure. The first thing you want to do is you want to have a preliminary analysis of your plant and understand what are your control objectives, like which are the obvious limitations, what are the objectives that you want to reach, okay? The second step is that of modeling. We haven't stressed a lot the modeling in this class. There are specific courses dedicated to system modeling. We have talked about, we have seen though that there are different approaches to modeling a system. We said that all models are wrong, in the sense that models are by definition a simplification of reality. And that's good, because as engineers, we care to focus on specific aspects, not to describe the truth, whatever that is, of what is actually going on. We want something that is useful to achieve our goals that have previously been defined as control objectives. But of course, depending on the specific plant, you might have different levels of complexity that your minimal model, your minimal useful model must have in order to describe the dynamics of what is going on. So we saw that we could use linear time invariant seesaw or MIMO systems. We haven't talked at all about the linear time variant part of things. You can imagine an x dot equals ax plus bu, where the a and b matrices change in time as well. Why not? We have assumed they're constant, but it could be x dot equals a of t times x of t plus b of t, u of t, right? And same thing for the output. That's a whole new family of stuff that at some point you'll have to look into, we haven't addressed. We touched upon the nonlinear systems, but when you do linear theory, linear is a very small subset. Nonlinear is, so linear is something very well defined that follows specific properties. Nonlinear is everything else. It's not like another subset of things that satisfy specific properties. Nonlinear is a general thing, a general term to say not linear, right? So everything else. And therefore, it's difficult to generalize when it comes to defining procedures for control of nonlinear systems. There are some, of course, the same concepts of stability, of performance and stuff can be defined, but really the tools become more complex, and each nonlinear system has a behavior, a personality of its own, and needs to be studied on a case-by-case basis. So once we have a satisfying model, or what we think is a satisfying model of our system, we can move forward. And we say, okay, let's now talk about the control structure. What is the control structure? The control structure is about choosing. This is something that we always are assumed that it's given. Now, when you solve your exercises, you're told, take this plant. X dot equals X plus BU. No? But who chose what is U? Who chose what is Y? Y, sorry, no pun intended, but Y is the measurement, the one that is the one represented by the specific exercise that is given to you. If you as an engineer need to handle a plant, you have probably some degree of freedom in deciding which are the measured outputs, which are the controlled outputs, what are the inputs. It really depends on practical things. You have actuators, you have sensors. The sensors you have available, what can they measure? Maybe they can't measure exactly what you want. Maybe you can choose. Maybe you can say, no, I can put a cam and say you want to measure, you know that your control objective is to, I don't know, control the temperature in a room, right? We could put a thermometer at the center of the room, or we could put an infrared camera at the corner of the room. They both measure temperature, but they're very different, right? So the process of choosing what are the best outputs and inputs for a system is not to be given as granted. And there's something to say about this, and we will talk about it a little bit later. Once the control structure is designed, so once you have chosen basically what the inputs and the outputs are, what the B and C matrices are, if we're talking about linear systems, then we step into the control configuration problem. The control configuration problem, we have touched upon some things. The control configuration is more about how do you partition your controller. We haven't even started talking about what controller are you going to use, okay? PID, LQR, whatever. This is, up to now, this is irrelevant. The control configuration is like, which inputs do I link to which outputs, okay? How is the best way to, how many controllers am I going to use in this plant? Are we going to put them in parallel? Are we going to put them in cascade? Are we going to use the decentralized approach? Are we going to try to decouple the system? Are we going to do a cascade-based thing? We haven't talked about cascade control. But so there's the problem only of deciding which inputs go and control which outputs is non-trivial. It's the input-output pairing problem. We have seen that through, for example, a simple tool as the relative gain array, we can understand which inputs are more effective in controlling which outputs. But there are many variations on the theme on that as well. So this is another issue that needs to be decided at this point. So once we have our model, we decided which are the inputs and the outputs based on the sensors and actuators we have available. We decided how to link the different inputs and outputs. It's time to decide, based on our original control objectives, how do we transform that general task we want to achieve into actual specifications, okay? So how do we define the performance measures that we want to achieve? How do we model the uncertainty and the problem, okay? So how do we define the actual mathematical specifications that the controller should meet? Only at this point, we can start thinking about, let's design a controller that fits in the structure we have defined before in order to meet the specific performance criteria. And at this point is where you get to choose, okay, do you want to use PID? Do you want to use LQR? Do you want to use loop shaping with the lead lag networks? Do you want to use a crazy H-infinity control? Do you want to use model predictive control? Or do you want to use the other 172 control approaches that we never even mentioned in this class? And probably you'll never hear of unless you do a career specifically on those things. But there are really many different kinds of control solutions that can be used, okay? So once we have chosen the type of controller we want to use, and we have designed it in order to meet the specifications, the analysis part kicks in. So the analysis part was the whole first half of the course. Now we finally have a model of the plant. We finally have a controller. Let's check if the specifications are met. What if they're not met? What if we design our controller and LQG and everything should be fine, but then we try and see what happens and it's not robust. It doesn't work in all the spectrum of cases that we care about. Well, in that case, what you have to do is you have to go back either to your performance specifications or to your controller design and reiterate until you're happy. If you're happy, then you move on and you say, well, are we ready to go? No way. The next step is take all this, this controller you have designed and simulate it. Simulate the behavior of the operation, okay? How do you simulate stuff? You simulate it either on a computer or you build a pilot plant and you test it on the pilot plant, okay? We have not touched at all on the simulation part of things. Just a couple words of caution. So simulations are when you basically write a computer program that tries to replicate all the model and everything, and you can think about, I don't know, MATLAB or Simulink as good tools to do this, but there are plenty of other ones. Simulations are great. You can really simulate pretty much whatever you want. Nowadays, computers are powerful enough to pretty much simulate whatever you want. But simulations are doomed to succeed. Okay, this is something that needs to be understood very well. In simulation, you have total control on everything that is going on in the system. Okay, you know everything once you simulate it because it's all running on your computer. A simulation just runs the problem that you set up. If by mistake, for any reason, you forget to put in something that you couldn't even imagine that was going on because, I mean, maybe you didn't realize that there was some crazy physical interaction with a nearby plant that had nothing to do with the plant you were given to control that somehow affects the system, your simulation will always work in the end, okay? Your numerical simulation, your computer-based simulation. And that might make you feel confident about your controller actually working. But that's not always the case. So simulations are good tools. Use simulations. Especially use simulations to make the situation as complicated as possible, but remember that you have total control over simulations, and that's not necessarily a good thing, because simulations are doomed to succeed. And in fact, if you have for really important projects, let's say plants that are very expensive, let's say you want to send a satellite in orbit or something like that, satellites that take 20 years to build and cost billions of dollars, you don't run a simulation. Or yeah, you run a simulation, but then you even build a fake satellite that has the same structural properties, mechanical properties without all the expensive payloads on it, and you actually run all the tests on the pilot plant. Okay, you try to replicate the physical system as well. So you do all your simulations, and you try to, and you iterate until you are happy. If you're not happy about the result of the simulation, after you already ran into the inner loop of redoing your performance specification and controller design, what is there left to do? Well, if this doesn't work, you need to go back to the modeling stage and repeat the process, okay? You add or remove different, you make your model less simple, and you try to re-go through the whole process and see if it works. If finally you get to a point where all your simulations seem to give satisfactory results and you're happy about your design, are we done? Not at all. Now it's about the implementation part. You made everything work on the blackboard and on your computer, okay? This still has very little to do with the actual plant that you have to control. So at this point, this is the point where you have to choose how to implement your controller on the actual physical plant. So you get to choose the hardware, and you get to choose the software to do all of this. You might think about, but what do you mean by choose the hardware? You already decided what the sensors and the actuators are. But yeah, sure, if I want a camera, there's 2 million different cameras, okay? And each camera has different properties. So you really have to, at that point, choose the exact model specification of your cameras, of your sensors, of your microcontrollers. Are you getting a Raspberry Pi? Are you getting an Arduino? Are you getting whatever it is? What kind of code do you want to use? Try implementing the same thing in Python or in MATLAB or in C++, you get completely different results. Some languages are more effective from some purposes, others from others. So this is completely beyond the scope of this course, but the implementation step is where you, A, choose your hardware and software, and B, you deal with the problems of implementation. We talked about discrete time systems, right? So we know that there are some inherent limitations in the implementation. So those have to be addressed. Every time you run any of the controllers that we've talked about, now, take an LQG. An LQG needs to compute what the gains are, it needs to compute what the estimates of the states are, it needs to move all registers back and forth, needs to do computation in order to get the variables that we just write as equations, okay? Because it's a discrete time process, it's not a continuous time process. What does it mean? It means that latencies are introduced. Delays are introduced, okay? Because the processor needs time to do the necessary computation to actually provide you the number you need, okay? And of course, if you're doing a single input, single output system, that might require nanoseconds and you don't even care about it, okay? But there are situations, take for example a DuckyBot, where the inputs are images. To extract from an image an actual state estimate, there are a bunch of different steps in the middle. These steps require a number of processing stages, okay? And at the end, between the image that comes in and the state estimate that comes out, maybe it took half a second, okay? Half a second is a huge amount of time if you're controlling a car that is driving around, okay? So that's when you have to deal with these nuisances. You have to deal with the time delays. You have to deal with, for example, once you've chosen your hardware, with the actuator saturations. Maybe you're using saturators. I don't know, the DC motors that we have on the DuckyBots. Well, you can't control them in a continuous manner, right? It's a PWM, a pulse width modulation-based approach. It's digital control. There are only discrete states of actuation that you can use. There's lots of details, and remember that the devil is in the details. Like, everything can be look fine in general, but then things work only if you address detail by detail everything that is going on. Once you're happy about the implementation, are we done? No. Then you actually take your whole control structure that you designed up to this point. You plug it in the actual plant, and you'll notice that things are slightly different. So there is a last stage where you do testing, validation, and tuning. So the testing typically means that when you're applying a control system, typically you have a bunch of different steps. You have, like, generally speaking, components, components, subsystems, and systems. So you want to start from the bottom and validate each one of these blocks. So validation means you want to make sure that the implementation actually behaves in a way that is predictable by you, because you is how it was designed. You want to see it in practice behave in a similar way to what you have designed. And you have to start from the bottom, do one component at a time, then put them together. You'll realize that there are hardware interaction between the different levels. And this is what you will study as you go onwards in the classes of, I don't know, embedded systems or robotics in general. Now, how is robotics different from control systems? Well, it's different because there are system-level interactions. Like, you can spend a career in each one of these blocks, the ones of the control loop, like designing a controller or designing an estimator. There's like two different careers. But then when you put things together, funky things happen, okay? So there is system-level interactions, and this process of validation, which is something that we have not addressed in a formal way, is basically the testing of everything bottom-up in order to ensure that things work. And often you have to tune online a little bit your original design to actually get the system to work as you want. Only at this point, you can then proceed to operation. So in all of this, the knowledge we have, how does it fit in? Well, the green stuff is the one that we pretty much addressed in a not complete, but let's say we have enough knowledge at this point of these things in order for you to go and open the right books and check the right stuff and be aware of the problems that are behind these different components. As you see, there are some of these blocks that we haven't really talked about at all. So you wouldn't be able at this point to just get a plant and go and design a controller about it, right? There are some things that we touched upon a little bit. Really, we scratched the surface. We talked about nonlinear stuff. We mentioned, for example, feed-forward and why is it important and why not, but we absolutely didn't go into details of how to do feed-forward control. There are courses only on feed-forward control. Only the ones of you that actually dealt with the ducky bots have some idea of what are the challenges of implementation and how the tuning works. How much time have you, on average, spent tuning the coefficients of the various controllers to make them work? You know what I mean, right? So, but still, you see, there are lots of things that we have not talked about yet, in particular, the control structure design and the simulation. So simulations, we're not going to be dealing with it in 20 minutes, of course. This has to do a lot with numerics. Take a numerical, numerics course. How do you solve differential equations with computers? How do you run optimizations with computers? There's lots of literature, lots of things to say there. And this concept of control structure design, in the sense, we always were given inputs and outputs. Is there a way, some guidelines, some general high-level rules of thumbs that we can follow given a plan to understand what are the best controlled inputs, controlled outputs, or measured outputs and inputs? So now I will just give you a little bit of an intuition about how to go through the control structure design. So the fundamental questions that we're going to address is, how do you choose the control variables? How do you choose the measured outputs? And how do you choose the measured inputs? And of course, we won't have time to go into the sensors and actuators because it's another course. So what is a control variable? A control variable is something that you want it to follow a reference trajectory. So you, at the very beginning of this whole process, you decided what your control objectives were, what your final objective, what your task that the system has to follow is, right? So, but up to now, in all the loops that we've designed, you might recognize this. This is the first time that we write the control loop that you've seen a million times up to this point without equations, so it might not look familiar, but it's the same exact thing we've been doing up to now. It's the control, the plant, the feedback, and we understood at this point that pretty much we kind of always want an estimation, a perception module in. So by the way, I used the bar here to indicate alternative terminology that you might find. The more you go forward, especially in the field of robotics, they tend to use the second word to describe what we use the first word for. So instead of estimation, they would call it perception. Instead of inputs, they would call it commands. Instead of estimate, they would call it a belief. But they're fundamentally the same things. And we always assumed that the reference signal was given, right? But is that really practical? So imagine a real problem, right? You have an autonomous car and you're driving it in a city. What's the reference signal? Like, what do you mean about reference signal? It changes, the environment changes. You have to drive. Maybe there is a pedestrian crossing the road. There's what not happening. I mean, it's a dynamic process. So the reference by no means can be known before you even start the whole process, right? But it cannot be known a priori. So what typically happens is that there's another block here that's called the planning block, okay? There's a layer, let's call it more than a block, that produces the reference signal on the fly, okay? So before we even get to choose what our control outputs are, we need, since the definition of a controlled output is something that follows a reference, we need to understand where does the reference come from, right? So you'll see that often control systems have different layers, different hierarchical layers, and the reference signal is always the output of the layer above it, okay? So in this case, we can imagine this planning as a general supervisor, an optimizer, let's say, of some intelligence from above that tells us what is the objective to follow on the fly. And the other layer, which is the one we've been studying in the last two courses, which is the control layer, has really just the task to implement what is the decision-making process of the planner, okay? And just to give you an idea, now, when are reference signals easy and when they're less easy? Now, try to imagine this is a cruise control kind of a system. Here, it's the easy case. Your reference signal is basically go straight, okay? Just stay in the lane. That's relatively straightforward. Now look at this. We are moving in a cluttered, uncertain environment. We have cars parked on the side of the road. We have people crossing the road. We have kids that could start running across the road at any time. It's a much more messy situation. So how do you decide on the fly what is the reference signal that your controller layer should actually implement, right? So, of course, we will not go into details of this because this... Question? Yes?
Out of curiosity, that on the right, is that already an autonomous vehicle?
Yes. Yes. And this is, of course, all computer vision based. The intermediate steps are that you start identifying what different objects are. So you put bounding boxes around them. You see, so the red boxes might be obstacles you want to completely avoid. So the reference signal has to be defined on the fly in such a way that you avoid hitting other cars or other people. The green boxes might represent instead information that is useful to you, signals you have to understand, how that give you, that restrict your domain of possibilities. For example, I don't know, if there is a no right turn sign, it means you can't turn right, okay, something like this. And the green represents just the field of view of the specific sensor. This, of course, is some vision-based stuff, but I wouldn't be surprised if there's LiDARs and other sensors involved in the process as well. So without going too much into detail, because this is something you will, for example, have a lot of opportunity to get your hands dirty with if you follow, for example, the Duckytown course, Autonomous Mobility on Demand, that's going to happen next semester, but at master level. Just for you to know, Emilio Fezzoli is kind of like his most cited paper is a sampling-based algorithm for optimal motion planning. Okay, this is a real problem, and the professor that should have run this course is actually his most successful paper is exactly on this. Okay, so how to determine a reference system on the fly. So this, of course, is, I mentioned the motion planner, but there are many other layers. The motion planner could be just this part here, so determining what is the trajectory to follow. But just to generalize, we could have other layers. We could have a behavioral layer, something that tells us, look, depending on the different situation we are in, then we have to run a different motion planner or have to have different kind of control decision-making processes going on. And even before that, there might be even a bigger picture. So there might be different layers in a control hierarchy. And this just to say that the reference signal that's our control out. Don't forget what the forest is. We're trying to decide what is the output we want to control given a plant, right? It's the one that follows a reference. The reference is always defined as the output of the previous layer, okay? And these are real practical problems. A Duckybot is doing exactly this in the back, and you don't see it. So now let's try to imagine different circumstances. There might be some cases in which it's easy, it's obvious to, because of the physical setting, what is the stuff you need to measure based on your control objectives. Let's say you want to control the temperature in this room. Well, guess what? The objective is controlling the temperature in the room. What do you want to measure? What do you want to control? The temperature in the room. Plug a sensor somewhere, a thermometer. You're measuring at the output, which is the same variable you want to control. It's an easy problem. No, not much to be said. Imagine instead that you want to bake a cake instead, okay? Now, baking a cake, you take your cake, you put it in the oven. What is a cake? What is a good cake, right? What's the control? The control task is getting a good cake. What do you measure of a good? How do you measure goodness of a cake? I mean, it's not straightforward, right? It's not obvious. What is the relationship between the controlled outputs, the measured outputs, and the final objective you want to reach? And so how do you go about doing this choice? Is there a standardized method? So the key idea behind this, and this is a powerful idea that will come up maybe in several years from now for you if you choose to go in the research route. Hopefully we will have been solved, the problem will have been solved by then. But the idea is that you choose a control output in such a way that, supposing you already have the input that is selected as well, you maximize the satisfaction of a specific task, okay? So it's all based on what is your final objective. You have a final objective that is well defined, and then you go backwards and you make your design choices in such a way that you maximize your final task. So under a bunch of simplifying assumptions, the idea here is just giving you guidelines, very high-level guidelines. It's not proving anything. Suppose that we have a system, a relationship between inputs and outputs, that it's evolving fast enough that we can ignore what the dynamics is and just pretend it's always going at steady state. Now, this is a good approximation, for example, when you do good assumptions, when you, for example, treat with ducky bots, you have these electric motors. Now, the DC motors are the ones that actually move stuff around. Well, DC motor, once you provide the voltage, pretty much goes at steady state immediately compared to the dynamics of the system. So you can neglect the dynamics and just consider the input-output relationship as a static relationship where there is some gain, G, a steady state gain that relates what your inputs and outputs are, okay? So suppose you have this relationship. Well, then the guidelines for deciding what your outputs are is you choose your outputs such that G is large. That is, the effect of your input on that output is big. You want to be able, with small variations of your input, to have big variations of your output. Why? So that you have more control power, so to speak. It's not technical, this thing. It's just a way of imagining it. You want to have a good grasp on the output and be able to move it around a lot so that you can improve controllability. You want to choose controlled variables that are weakly affected by disturbances and uncertainties. That's because one of the fundamental objectives of a control system is rejecting these disturbances and uncertainties. So it makes sense to choose, in first place, outputs that are not affected in a big way by these disturbances and uncertainties. And finally, you want to have choose an output for which, as much as possible, it's relatively easy. I understand this is not, it's very high level, but it's, without going into details, it's of a specific system, not much more can be said. You want to try and keep the tracking error as small as possible, because the tracking error will bring you away from the optimal situation of achieving your final task. Just to give you an idea of how to formalize a little bit this process, this is not meant to be rigorous, but suppose you have always your control objective is getting a cake to be good, right? Well, we can't measure goodness of a cake, but we can create a scale, and we can say, look, let's make a scale from 1 to 10, and let's say that 10 is the perfect cake, okay? It's a cake that is crunchy on the outside, soft on the inside, but it's cooked but not burnt, and it's perfect, and everybody likes it. And let's instead define 1 as the cake that is completely burned, and it's completely the control objective, that is getting a good cake, is failed for all means and purposes. Well, then we can create a cost function, an objective function that we want to minimize. Why? Because we're good at minimizing things. We have the math for doing that. So once you have your quality cake scale, you can just put a minus in front of it, and now maximizing your quality of the cake means minimizing the opposite of the quality of the cake. It's just a trick. So suppose that there exists an optimal input. Consider inputs and outputs are related, right, by that G relationship that we said before. So if we find the input, we are implicitly finding the output as well. Suppose that there exists an optimal cake, an optimal input that provides the best possible cake ever, okay, like a 10 on the cake quality scale. Then you can set the problem of finding the output to control as that of finding the input that gives you the best optimal cake metric. And the metric, of course, you can define it as you want. So this is a very general approach. Now, you have to do some assumptions here. You have to say, okay, your references are not affected by the disturbances. In all the control loops we wrote, we never made the disturbance affect the reference, right? But in some cases, that could actually happen. There are tricks you can use to avoid it, but let's suppose for now that the disturbance does not affect the reference. Then what is the objective? Well, one obvious thing that we can say is like we would like our input to be the optimal input, right? It seems obvious, but it's going to be useful. Because what's going to happen is that because of disturbances, because of noises, because of model uncertainties of the plant you have, you don't know exactly. You'll never get the optimal input. No? So if we focus on, let's suppose we have an input, okay? An input U that is different from the optimal input. How much are we losing on the optimal cake quality metric? Well, whatever the cost function is, if we make some technical assumptions that are beyond the scope at this point, for example, that the cost function is twice derivable and things like this, differentiable and stuff like this, we can do a Taylor expansion around the optimal point, right? So If it's the optimal point, well, a Taylor expansion, you all, of course, know exactly what it is. You're just evaluating the function at a specific point, and you're creating a linear approximation. And we can choose how many terms to use. So the first one is going to be the optimal value, which, whatever it is, we don't know. The second one is going to be a function of the gradient of the cost function evaluated at that point. But because of optimality, it means that the first derivative is 0. Then you might have a second-order term, and you might expand this as much as you want with higher-order terms. So if we go and check, so the difference between the input that we're using and the optimal possible value, this is the loss in cake perfection, okay? It's like if you have the optimal value, you will get the perfect cake. But we'll never have that. We'll have some other input. So how much are we losing with respect to the optimal situation? You can evaluate it based on, it's just this term here, the second term. So it's the difference between J and J optimal. So you bring this on the other side. This goes to 0. You just have this other term here. Now you just leverage the equation we had before, that is the relationship at steady state between inputs and outputs. And the bottom line is that you can express the controlled, you can determine what the controlled output, the best controlled output for your specific system to be based on a standardized procedure. And under some simplifying assumptions, what you really want to do is minimize this quantity here. So you see that this quantity here is proportional to the inverse of the gains. And that's why we said, hey, we want G to be large. Now you want to have a good power of the input on the output. Why? Because if G is large, then G inverse is small, right? So if G inverse is small, this whole term is going to be small. You're not going to be far away from your optimal cake perfection. Or you want this difference y to y minus y optimal to be perfect. No, so you can play around with these terms here and show that this is a function of two, an optimal error and a tracking error. And that's what led us to say before that the other two considerations on choosing an output. So without getting too much in the details here, the idea is, how do you choose your controlled outputs? Well, first define what your final objective is. You've got a task you want to achieve. You've got a final goal. Based on that final goal, you'll step it back, having some assumptions on what is the dynamics, the relationship between your inputs and outputs, and you can use a formalized approach to determine what your outputs are. What about the inputs and the measurements instead? Having a formalized approach to choose what the best inputs and the best measurements are are there any comments? Sorry, I shined the laser on you. What are comments, questions, or doubts?
I got a question.
Yes.
Why is it minus C and not just plus C?
Because if you want to, so C is the cake quality, okay? Higher values means better. We like to minimize instead of maximize. So if I want to pose the problem as a minimization problem, then I define the inverse of it. So if I minimize the inverse, I'm actually maximizing the rest. It's just a mathematical trick. So how do you choose measured outputs and inputs? Well, the measure outputs, these are really just general guidelines. You want to have something that, of course, has a strong relationship with the controlled output. Ideally, it's the same, like the example of the temperature in the room. If you can measure directly what you control, well, that's the optimal scenario. Since you want to do disturbance rejection or noise attenuation, you want to or disturbance rejection in particular, you might want to be able to measure things that can detect the appearance of the disturbance as quickly as possible, so that your control system is able to compensate. And most importantly, we saw what is the profound implications of observability and detectability. No? So on determining the state, the state estimates, and therefore implementing efficient controllers. To do so, you want to make sure that when you measure stuff, you're addressing the problem of observability. Don't measure quantities that make your variables of interest unobservable. Otherwise, you're going to have problems, especially if there are unstable modes in your plant. So the minimum you have to do is make sure that you choose your measured outputs in such a way that the system is detectable so you can stabilize the unstable modes. And basically, similar considerations apply for the inputs. You want to have inputs that have large effect on outputs, the same thing we just said before. You want to have inputs such that the system is reachable, especially if your open loop plant is unstable. The first objective of a controller is stabilizing the plant. So if you choose inputs that go and poke the system in places where you can't actually reach the unstable modes, well, there's nothing, you failed before you even started. There's no controller in the world that's going to help you. And then you want to make sure that your Inputs are placed in a way that they're dynamic, in a dynamical sense, close to your measured outputs. That's kind of tricky to explain, but the idea is that if there is a dynamical, imagine you have a fishing rod, okay? If you just measure the position of the tip of the fishing rod, and your inputs instead are the torques you give at the base of the fishing rod, well, you have a big dynamical distance, right? Because when I give the input, the output, there's going to be some flexion of the thing, and the output is going to move after a while, in some sense. Well, if you formalize that problem, you'll realize that with that choice of inputs and outputs, you have non-minimum phase zeros in the system. So only by picking where your inputs and outputs are, you are introducing or not non-minimum phase zeros in the system, and that, as we know, might cause problems. So I'm nearly done. I guess I wanted to give you extra minutes, but instead it didn't happen. Oh, no. So now we've talked a little bit about most of the things that are going on here. I have one slide left. Please be patient. What are the gaps in knowledge? What are the next steps? So you have to sit in other courses. I'm sorry, you don't become a control engineer with 2 courses. You need more stuff under your belt. In particular, I can't stress it enough, you need laboratory experience, embedded systems, deal with hardware, deal with software, code stuff, sit in labs, take all the possible experience you can with direct hardware, because the devil is in the details. You'll realize how many details are relevant to specific plants. System modeling. Well, all the different trade-offs between choosing different ways of describing mathematically physical phenomena. What about linear time variant Caesar MIMO systems? What about different families of nonlinear systems? We did all of this with a deterministic formulations, okay? You could rewrite this whole course based on probabilistic definitions, okay? Given an input, there's a X doesn't represent the position of your system. It represents the probability that the position is in that point. Okay, everything changes. Okay, so you could rewrite this whole thing just from a stochastic perspective. That is actually effective. The most you go forward, all the Duckybot is based on stochastic representations. As far as controller synthesis goes, we have described some controllers. There are many more. Optimal control is a full exam, full field, plenty to say. Model predictive control is incredibly useful, incredibly practical. There's a dedicated course sitting in that as well. There are many other control algorithms that are worth learning. Iterative learning control. There are controllers that can learn depending on repeated operations, and they can change their structure. We have always talked about controllers that we set a problem, we get the controller, but the controller never changes in time. Can you write a controller that adapts itself in time? It's called adaptive control. Another course, go sit into it, okay? So there are many different approaches that all could be relevant in different situations. Estimation. So we saw how powerful state feedback is. Estimation, as I mentioned plenty of times already, it's super critical, super important. 2 or 3 courses out of that. And then dedicated courses on discrete time. We did 1 class on discrete times. That's absolutely not enough. That's just pointers on what is going on at a fundamental level. There's much more to say. So if you have to remember 5 things out of this course, what do you want to remember? MIMO systems are challenging because of interactions, okay? But fundamentally, it's the same thing going on at a more interactive way. All models are wrong, but some are useful, okay? When you model stuff, you never get it right. There's always the problem of robustness. There's always the problem of model uncertainty, and that's a make or break deal when things actually work or not. So be careful of model uncertainty and address the robustness problem. State feedback, it's very powerful, opens a can of worms. Estimation, deal with it. You can't survive without knowing more about estimation. There are complex mathematical machineries. We saw all the big machines there, but at the end of the day, we're always doing the same thing. We're always shaping sensitivity functions because that's the fundamental truth that's going on in a control system. And finally, there's lots of mess going on the implementation side of things. So don't just do things at the blackboard, but play around with hardware. Thank you very much.